Hey kids, welcome to our lesson on Cauchy Euler differential equations. But before we do that, we are going to look at this differential equation, find and classify any singular points. And I hope you realize that's kind of a silly question because p of x is equal to the constant function 1, which will never equal 0. Therefore, there are no singular points, which means I can build a Taylor solution of this differential equation around any center, and I'm asking you to center it at 0. So I'm going to skip ahead to the part where I would have already shifted my indexes so that I had an x to the n. Or not shifted so that I got x to the n with the second derivative, the first derivative, and distributed this 2x in. So again, I'm skipping some work here. Where I had x to the n minus 2, so I added 2 all along here so that I got an x to the n. In here, I had x to the n minus 1, but when I distributed in the 2 and the x to the first, that automatically made that an x to the n, and this, of course, was already an x to the n. So now I have my highest index of n equals 1. So I'm going to go ahead and pull out an n equals 0 term from here so that I get n equals 1 and an n equals 0 term from here. And when I do that, I got 2 times 1 c sub 2 x to the 0. And then I got a plus, plugging in 0 there, I got c sub 0 x to the 0. And over here, I have a plus 0 x to the 0. So I'm going to equate those and say that I have 2c2 plus c0 is equal to 0. Therefore, c sub 0 is equal to negative 1/2. I'm sorry, c sub 2 is equal to negative 1/2 c sub 0. And I have c sub 2 already in terms of c sub 0 because remember, I want all my coefficients in terms of c sub 0 and c sub 1 since this is not an initial value problem. Now I'm going to go and collect all of the things in front of, now that I've shifted all my indexes to 1 because I took out the n is equal to 0. I am now going to equate all of these and set them equal to 0. So I end up with and then solving for the highest coefficient there. Write that a little bit nicer, factor out the c sub n. So I don't need to start at n equals 0 because I already have my c sub 2 term. So I can now use my expression, right? I can now use this to start generating c sub 3. So when n is equal to 1, that's going to generate c sub 3. And c sub 3 is going to be c sub 1 over 3 times 2, which is going to equal 1/6 c1. Then I'm going to do when n is equal to 2. Whoops, that's a 3. That's going to cancel out. And remember, c sub 2 is equal to negative 1/2 c sub 0. So I have negative 1/2 c sub 0. That's what c sub 2 is. And then times 1/4. So I end up with negative 1/8, right? C sub 0. I'm going to let you go ahead and figure out some of the rest of your terms because I asked for the first 6. And I'm just going to write what I have here. What I ended up with was y was equal to c sub 0. Right, because that's plus all the functions in front of c sub 1 ended up being x, right? Because when I write my power series, right, c sub 0 x to the 0, which is just 1, c sub 1 x to the first, and then the rest. Now this is all I wanted. Actually, I wrote more, right? First 6 terms, and I gave 1, 2, 3, 4, 5, 6, 7 terms. So probably didn't need this little extra one here. Could have just done 3 and 3. And that's where you would stop. But I just want to show you for emphasis sake, if I had given you, or just for demonstration purposes, this link is to a Desmos that has these 2 functions with their rules in it with an initial value problem. If I told you that y of 0 was equal to 1 and y prime of 0 was equal to 1, that's what c sub 0 and c sub 1 is. So I'm going to replace this with 1 and this with 1. And then I came up with a summation rule for these terms, which you don't have to do, but I just went in order to plug this into Desmos. That's what I needed to do. So I'm going to switch this over to the Desmos screen. And I want you to look at what I have here. In red, I have the series with, I don't know why I did the C sub 1 term first, but I have x plus, after the x term, I got a rule for the rest of those terms, right? The 1/2 x, 1/6 x to the third and 1/24 x to the fifth, those odd powers. Here was the rule I got, and I just took it out to 10 because obviously you can't graph Desmos, can't have this go to infinity. And then I made the coefficient b equal to 1. Down here, this was the c sub 0 terms where I had 1 minus half x squared, and then I could figure, and then I got a rule for the rest of it here and graphed it from 1 to 10. And for each time I made my initial condition b is equal to 1 and a is equal to 1. So here are the two separate power series solutions from, I terminated it going from 1 to 10, but still, notice that when x is equal to 0, if you add red and blue, you're going to get a y value of 1. So the actual solution is the linear combination of this blue curve and the red curve. If I turn those off and turn on, down here is both of them. You just can't see, right? In here, I've added the second series. So this is the graph of both of them together. There's the power series solution centered at 0 for the differential equation that I gave you. Right? Pretty cool. All right. Notes. Cauchy Euler equations. These are second order differential equations that have a certain pattern, and because they have their pattern, even though they have a singular point at, I hope you can see where, we're going to get a solution, and we're not going to use power series to do it. So first, find and classify any singular points, right? P of x is equal to ax squared. So getting the differential equation into standard form means I have y double prime plus bx y prime plus cy is equal to 0. But I would divide this by ax squared and divide this term by ax squared as well. This is now little p of x. That is little q. So take little p of x and say that's b equals b over ax. And remember, my singular point is anything that makes p sub x equal to 0. Forgot to write that down first. So don't make your center equal to 0. That's singular. But now I want to determine what kind of singularity I have. So you look at the power of x minus 0 to the n in your denominator. N is less than or equal to 1. Check. Here I have x minus 0 squared. N is less than or equal to 2. Check. Therefore, this is a regular singular point with a center at 0. So I'm going to say that, remember we said with regular singular points that we can find some ways around the singularity at 0. And with Cauchy Euler, I'm not only going to be able to still build a power series, still get a solution. I don't have to use power series to do so. That's if I recognize the Cauchy Euler form. So here he is, Cauchy. I forgot his first name. We can avoid constructing a power series if the power on x matches the order of derivative of each term. So here's what I mean by that. The power on x is 2, and the derivative on the order of the derivative is 2. The power of x is 1, and the order of the derivative on this term is 1. The power on x is 0 on this term, and the derivative on y is 0. This is the 0 order derivative, right? Since those all match, I am going to be able to use Cauchy Euler's method instead of constructing a power series. So Cauchy Euler equations, remember we're dealing with a second order differential equation of this form where P, Q, and R, right? When they were constants, I want you to remember what we did was we found a characteristic equation. We solved for the R, right? And we always, since this was second order, we were solving a quadratic. And then we created the linear combination of linearly independent solutions. And they looked like this, right? When we got real but not repeating solutions, real non-repeating. This was real and repeating. And we had to multiply by this factor of x to make sure we had linear independence. And then if we had non-real, and we didn't have to worry about repeating non-real because we were dealing only with second order. So if we got non-real answers, they were the complex conjugates, right? So the P, Q, and R of Cauchy Euler's looks like this, right? Where capital P is ax squared, and the power on x matches the order of the derivative. The Q is bx, and the power on x matches the order of the derivative. And the R is the constant in front of y with the 0 derivative. So, in order for this equation to equal 0, the derivatives, which by the way have x squared and x, the derivatives need to be related somehow in order, right, for me to solve this differential equation to show that I have a solution to the differential equation. So what if I just guess? What if I say the solution was x to the 4th? If the solution was x to the 4th, what's y prime? Truth? What's y double prime? Right? Now, let's plug this in to this differential equation. Is this a Cauchy Euler differential equation? Ax squared y double prime plus bx to the first y first prime, first derivative, minus 16 power of x of 0 and 0 derivative. So look at this differential equation, and I want you to check and verify that the solution to this particular Cauchy Euler differential equation was x to the 4th. So what are you going to do? You're going to multiply this by 1x squared, right, to get this term. Then you're going to multiply the first derivative times 1x, and you're going to multiply the original times negative 16. And then you're going to see if that adds to 0, right? So 12x to the 4th, right, multiply, plus 4x to the 4th, multiply, minus 16x to the 4th. Does that equal 0? It does! Woohoo! So x to the 4th must be a solution of that differential equation. I didn't need a power series. Yay! So let's generalize this situation. Let's suppose that instead of me just randomly guessing x to the 4th, I just guess with a Cauchy Euler differential equation that my solution is x to this power r. I'm going to use that same thought process, and I'm going to take the first derivative and the second derivative, and then I'm going to plug it into the Cauchy Euler differential equation, which looks like that. So what do I need to do? I'm going to multiply y prime by bx and y double prime by ax squared, and the original y by c. So ax squared times the second derivative plus bx times the first derivative plus c times the original. See what I did there? X squared got matched with x to the r minus 2 and became x to the r. X to the first got multiplied with x r to the r minus 1 and became x to the r. And then I have an x to the r here. Good F word. Factored out x to the r and was left with this inside. That was Dylan and Grace. Sorry. I divided everybody by x to the r. So I divided through, and I was only left with this. And I distributed there. AR squared minus AR plus BR plus C. Then I took this term and factored the R out of it. Then I wrote it a little nicer. This, kids, is a characteristic equation right? This right here is the characteristic equation to get our fundamental set of linearly independent solutions to the Cauchy Euler. Oh my Lanta. What? So you want to memorize this. The solution to this characteristic equation will give us our set of linearly independent solutions that will look like this. And it'll follow a very similar but not exact pattern to when we had our regular second order, when we had constants in front of our differential equations, where if we look at this characteristic equation and factor and get R1 and R2 are non-repeating real roots, then our solution looks like this. It's not e to the r sub 1, it's x, all because the Cauchy Eulers start with that quadratic function as p of x. If it's a repeating, now what? This is going to blow your mind a little bit. I have the same root. Oh, this should look like, right? This is R1 and R1 because it's repeating. And this is the factor you multiply by to make sure you have linear independence. You can't multiply by an x because that's going to get absorbed here, right? Now, why it's ln of x? Your book does in this section. Your book shows a proof, which just involves rewriting, the solution and thinking about derivatives and then anti-differentiate and getting this term. But your book has a cute, right, and not hard to follow proof of why you end up with ln x. Actually, oftentimes you'll notice that your book doesn't use absolute value, just drops the absolute value and says, by the way, though, x is always greater than 0, right? So I'm letting x be, well, not 0, but I'm letting it be -2 if I keep the absolute value. I just don't want you to be thrown when you don't see absolute value, but you see that. Then case R, when I get non-real answers. Now the only thing I chose to use alpha and beta here because just to differentiate it from our regular A and B. So notice this time that again, I don't have e to the, I have x to the real component, and then sine and cosine to the coefficient of the non-real. And then I have to multiply by ln again of x here. Crazy. Let's try some. You ready? All right, first thing you want to do is pull out A, B, and C. Oops, sorry. I don't mean that to be x squared. I mean that just to be 1. A, B, and C are the coefficients. So 1 in front of x squared, -3 in front of x, and +3 in front of the y. And now just fill in this equation. So I have 1r squared plus b minus a. What is b minus a? -3 minus 1 plus 3 is equal to 0, aka r squared minus 4r plus 3 is equal to 0. Factor. X cubed. X to the first. Right, that's where these went. Right? So I have a finite power series, if you will, right, without constructing the power series. Sweet. Done and done. Thanks, Cauchy. And Euler. Let's try another one. What's the coefficient of x squared? Coefficient of x. Coefficient of x to the first. Coefficient of x to the 0. Fill in your formula. 2r squared plus b minus ar minus c plus the -1 equals 0. Factor. Solution. C1 x to the 1/2 done. And you can always check our work, right? You can take the first derivative and second derivative and plug them back in here and see that you get 0. All right, why don't you pause the video and see if you can do these and then check with me when you're done. All right, so I'm just going to put up my factors here. So I got r squared b minus a In this case, I got r minus 2 repeated real factors. So don't forget here you have y equals c1 x squared plus c2 x squared what? Again, I don't care if you write it like this or you write absolute value of x. Really, it would depend upon my initial condition as to which part I used, right? So how about example 4? Example 4 is another example where I had repeated roots because I also ended up with r squared. 4r squared plus 4r, right? b minus a plus 1 is equal to 0. So I had 2r plus 1 squared. So my solutions were c1 x to the negative 1/2 plus c2 x to the negative 1/2, but times ln of x. Five. I think you can probably figure out what's going to happen here, right? I'm going to get 1r squared plus b minus a plus 16 is equal to 0. Therefore, r equals plus or minus what? 4i, which is really 0 plus or minus 4i. So there's alpha, there's beta. So my solution is y equals c1 x to the 0 cosine of beta, the real component of the imaginary term, for ln x plus c2 x to the alpha sine beta ln x. Or again, you can scratch that and just do this if you like. And of course, you don't have to write the x to the zeros, right? Because that's just 1. Example 6, be careful because notice that your center is not 0 anymore. Your center is 1, right? But I still have squared minus, I'm squared matched up with the second order differential equation to the first, term with the first order, and the x minus 1 to the 0, right? And my singularity point would be at 1. So what is my a? Right? What is in front of the squared term? A 1, right? What's in front of the thing to the first? What's in front of the thing to the 0? B minus a. This was 6 plus or minus the square root of negative 16 over 2. Which simplified to 3 plus or minus 2i. So my solution looked like x to the third power cosine of the coefficient of the imaginary ln x? No, not ln x. ln what? Aha! Snap. Be careful, right? Notice that what I was dealing with here was x minus 0, right, to the ends. So that's why you had x here and x here, technically x minus 0. So this time I'm dealing with center x minus 1 to the n. So be careful. X to the alpha sine beta ln of x minus 1. And of course, you could drop the absolute values and say x is greater than 1. Right? So be careful, because again, what we're doing is using Cauchy Euler's differential equation and the pattern that they found and discovered to avoid building a Taylor series around a singular point, right? And getting solutions without, that still are polynomials in terms of x. And again, when we have non-real parts, we still have the cosine and sine pieces. But before that, all the rest of them were all powers of x, right? Oops, sorry, I didn't mean to go that way. That is all. So enjoy the homework, and hopefully maybe you can do some of that in class. And it will not be due on Wednesday because you have the quiz on Wednesday. So we'll be doing the group quiz on Wednesday, and I won't be checking the Cauchy Euler homework until Thursday. All right. Have a great day. I will see you on Wednesday.